Here we are on the 20th class of Packet 4, Friday in February. And now, here is the packet organizer. Now it's available on Facebook, but I think I'd wait till the PDF comes out so it'll print off nicer for you. I'll put some on the porch. This is not due until Thursday next week. Actually, for you all, I think it's Friday. Yeah, it's Friday for you guys. So a week from today, you'll need to turn in your Packet 4. And then you'll turn in your Packet 4, pick up your test. Now the tests, I'm a little bit more, these major tests, I'm a little bit more careful with than I am the A test, you know. So more about that later. What I'd prefer you do is turn in your packet, and then when you do that, you'll pick up your test, and then you'll turn that test back in. And maybe when you turn a test back in, perhaps I can give you your packet back graded. I don't know if I can pull that off. Anyway, that's next week. So here it is. There's a 125-point packet. And that's just the papers. If you add up all these points over here, you'll get 125 if you include the take-home test. And the take-home test, you are going to turn in a paper copy of it. You're submitting the take-home test though by Tuesday, like everybody else. You're submitting that for a picture of it. And then you'll do your note credits. And I'm looking at your notes. I'm thinking probably 75 points sounds about right. That also includes your Packet 4A, your Test 4A practice problems. All that's included in your notes. And then the discussion class points, you wouldn't get any of those. Where you would get those, you would fill in the Zoom points. And some of you have gotten Facebook points as well. Now the packet should be, when you turn it in next Friday, it should be perfect. Okay, there's no reason why it shouldn't be perfect, because all of these have a key posted. Well, now it's up to, I posted 4.9. I'll post 4.10 Monday night, and I'll post 4.11 probably Tuesday night. Yeah, 4.11 will be Tuesday night. So eventually all these keys are posted. So you, like in class, they get dogs, right? They get stamps. Well, and then for you all though, for virtual, you submit me a picture of your work. And I pretty much look at that. I'm saying, did they try? And if you did, you're going to get a 16 out of 16 or whatever it is. But it doesn't mean you're right. So it's up to you to go in and now look at that and go, am I agreeing? You may have all the points for your weekly submissions and have perfect score there, but everything's wrong. Because it looked like, from my point of view, just looking at it, it looked like, okay, they're doing physics, they're thinking about it, they're working hard. That's what you're getting the credit for. So it's up to you to make sure that you're right. So you can already check 4.1 through 4.9. That's all available on Facebook. So you should check the key. Just put your paper there, check the keys, say, yeah, we agree, we agree. If we don't agree, then you need to ask me questions about it. Okay, so all of that's your cover sheet, and you'll staple that to the front of your packet. Sometimes virtual kids forget to do a cover sheet. Well, that's an automatic minus. You're down here without a cover sheet, you're at about a -20 to start off with, because I've got to see these checked. I hound them in class about it, but you all aren't in class. So these columns have got to be checked, either checked or not checked, but you can't false check them. But that's actually from the students asked me to put those boxes there, so they can kind of keep track of their packet as they go. But anyway, so any questions on the packet organizer before we get into today's topic? Okay. So in first hour, a question came up from the student wanted to go back and talk about the back of 4.9. This is 4.9. The back, so 4.9.3, which was the homework for them that was due yesterday. And he had a question about it. And so I was looking at it during first hour. And for one, it looks like some of this orange mirror stuff got through. I thought I'd killed all that. But they used to be called orange mirror equations or kinematic equations because they were actually put on a mirror. There was a mirror that hung from the ceiling. It's a long story. And we put them on the mirror, so they were called mirror equations. Well, I thought I've deleted mirror out of everything, and now I'm seeing it's there. It may just be in the key. It may not be on the sheet anymore. Anyway, if it's there, just take out the word mirror. But his question was not that. His question was that we have this equation. He said, but that's not the second orange equation. And I said, well, yeah, it is. He said, no, the second orange equation is delta x equals v naught t plus 1/2 at squared. And this equation is different than that. No, for one thing, if there is a square, if it's a second order polynomial, it's orange. I don't care. If that's the highest power, then that is a second orange equation. That is an orange equation. So this one, it's just not the same order. This 1/2 at squared, that represents the 3. Remember, coefficients are eternal. They are eternal truths. That 1/2 is eternal. It's always 1/2 a. The 3 is a constant. 3s are not eternal. That 3 it's transactional, right? It's situational. It's because we know the acceleration here is 6. And then the v naught t, that's your 4t. So we know our initial velocity is 4. And then we have this 8, and that's what really threw him. He said, wait a minute, but there's this 8 there, and that's not in the orange. There's nothing about it. And actually it is, because this says delta x. But remember, delta x is x minus x naught. So you can rewrite it. You can leave it as x as it is here and just put this is your x naught, just moved over to the right side of the equation. So this is more of the graphing version. And then that is what someone said, why don't we give it two versions? Why don't I just do one version? Well, because this version you see as an orange kinematic equation, as you'll see in textbooks as well, this is convenient for equations, because normally what you're looking for with the orange equation is the change in position. So I've thought about just not doing it that way, just doing it this way to avoid that. But the convenience kind of forces me to go back to the way it is. So that's what that talks about in the key. And then the rest of this you can look over, but you can look at this now. This is what I mean. You need to look at this. If it's not what you had, then you need to fix it, and you're fixing it for yourself. You're probably still going to get okay credit for me, but I will go through and I spot check. I will spot check some things in your packet, and if they're wrong, you're going to lose some points. Even though you go, well, I did it all. I got all the dogs. I mean, I got a perfect score here. Why are you kind of wrong? Because you're wrong. Because you never went back and checked with the key. So you will get burned on that. I don't check everything, but I do spot check some stuff. Okay, so yesterday in here, it was in here that we talked about, like in pink equations, we said as you go down, it's the derivative. If you go down to one below, derivative. But then as you go up, I think someone in here or somebody in third hour asked, what if you went up? What's that? How do you go up? And that's called antiderivatives. And so antiderivatives are just reversing the process, okay? And we've done antiderivatives in graphs. We did the finger dance here back in like October or something, where you look at the velocities, you can then convert those into accumulation of position. And so this graph here, blow this up a little bit, this graph here gives you this graph here, right? This comes from this graph, comes from this graph, or vice versa. If you go down, it's derivatives, but as you go up, it's antiderivatives. And if you apply border conditions to that, you get integrals, which that's an April thing. So I'll hold off on April to get full into that. But this does lead to this guy. Oh, not this. We did this yesterday, and that was a good exercise. Watch out for that one on the test. And then this thing. Now, this is what we did in here. But this was a surprise to the regular kids because they go, whoa, what's that third row here? And that's what we were starting to do in here. So now I made them do it today. So the third row is from now on, you're going to have three. I'll change the sheet for next year. And I'm making up a worksheet on this. But you'll have 3 boxes to fill in on next year's take-home test, where the third row is the initial condition. And that came up because somebody said, well, initially you have a jerk of 3. Nope, nope, nope. That's why I said, okay, you better talk about that. Remember, that's for the pink equations. Back here on the pink equations, that is 1/6 of jerk. That's the difference between coefficients and constants. The coefficient is the 1/6. The constant here is the 3. You see, coefficients are eternal and universal. Anywhere you go in the universe, there'll be a jerk. There's always a jerk. There'll be a jerk anywhere in the universe, and that'll always be 1/6 J naught, always. But the 3 is transactional. The 3 is situational. So 3 just happens to be the conditions of that particular problem. So you see the difference between constants and coefficients. Coefficients are eternal truths worth writing down. I'll put this in the book. Eternal truths. And these are situational. Okay, they depend. Okay. So then last night I was thinking about this and I said, we have beautiful patterns in, we have these, to go back here, we have these, where's it at? Yeah, we have these beautiful patterns. Take it all up to the sextet if you want. You can go to the octet if you want. But we need, and there are some equations associated with those. Those are very general equations. So now that we know a little bit more about power rule and derivatives, antiderivatives, now we need to develop a beautiful patterns for equations. So now let's look at a snap. Let's look at a situation. A snap is like a snap set. Okay, it's a set. It's a set of equations that go with a snap. And I want you to go ahead and write this down. This is not, I'm going to put this in a worksheet next year, but this is not in a worksheet this year. And the questions came up, I think, in first hour was, wait a minute, do we need to know this one for the test? And the answer is yes. It's not on the take-home test, but remember, I have a caveat there. As far as practice problems go, on the A test, the A test will only consist of problems like practice problems. But on the test, because take-home test has to come out so early, I can hold back 10%. So I can surprise you with 30 points out of 300, 30 points. And this right now, this is the greatest candidate for those 30 points. So write this down in your notes, in your piece of your notebook or notebook paper, write this down. And our object here is to fill in the boxes. It's one of the main things. The main things we're doing today is fill in these boxes, and then we're going to try and get 410 done. Okay. So I'll give you a second if you're watching the recording, write this out, and good exercise here. Good exercise. I said, no, you don't need to memorize, what's it, 5, 9, 4, 6, 9, 11, 12, 13, 14. You don't need to memorize 15 things. You just got to know the pattern, just like the beautiful patterns and graphs. Okay, and I didn't know what to call snap, what symbol to put for snap. I didn't want to use S, and I've seen different ways. I don't think anything. I think it's such an uncommon thing to go through a snap. People die, right? I mean, this right here is death. But to go through a snap is very uncommon. So you don't see. It's not like it's in the vernacular. So SN is what I'm going to use. So this would be snap knot. Now there's a proposal by third hour to call it snot. I'll take it. So the snot. So it's like, what's your snot? snap not, which tells me what's my initial snap. And so if it's a constant, the snap, if this is a constant snap, so it stays that way, it's flat right in the graph. So now we can follow the beautiful pattern. Beautiful pattern is this way, this way, this way, and this way. The same idea. So what will this box here be?
Would that be J naught?
J naught, thank you. So now we're on the pattern, we're on a roll now. That is J naught. Okay, now you get the idea. Therefore, that is A naught, that is V naught, and that is X naught. So that wasn't hard. You always end up, if you're in calculus, when they do an integral, and those that are in calculus will know this, you always do if it's a general integral, you do blah, 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 integral plus C. In math, they call it plus C. Well, that C is this plus, that C tells you your initial conditions. And so in physics, we're more specific. So what are we talking about? Acceleration? Okay, then it's plus A naught. Is it jerk plus J naught? Okay. That surprised me when I was in calculus. Oh, that's what that means, plus C. Well, then here's another pattern. If that's snot, then that's snot. Snap knot, snap knot, snap knot. Uh-oh, except we got to put in the coefficients. But snap knot does go in all those. I mean, give myself some room for coefficients here. Okay. Okay, so, and then also, might as well get all the stuff we can get. Also, that is J naught, J naught, J naught. Now be careful though, but give yourself some room for some coefficients. And then this is A naught, and V naught. Okay, now all we gotta do is add the coefficients and we got it. For this one here, for the jerk, there is no coefficients. I mean, it's like, if you look back at the pink, if you look at these pink equations, we use that as our template. So hold on a minute. Let me find it and scoot it over. Let's scoot this guy over here. Okay. So looking at the pink equations, we go back and forth. So the pink equations here, notice that in that case, it was J naught. The next one was J naught plus A naught. The next one up. And the next one's 1/2 J naught plus A naught plus V naught. So this then must be, this next one, where the coefficients go, there's also a pattern there. That must be 1/2 plus J naught plus A naught. And this is like the second orange equation, which was 2 above the base, 2 above the foundation, right? The foundation for the orange equation was A. The next one up was V. The next one up was X. So, and that was the general form of the X equation. But then now we go looking back at the pink, the next one up above the 1/2 was the 1/6 for the first one and 1/2 for the next one. So over here, then we do the same thing. 1/2, 1/6 for the snot, and then 1/2 for the jerk, J naught. And so those are also taking a diagonal pattern. These are understood ones. So those also take a diagonal pattern. So now that then for the X is 1/2. Follow the pattern. That is 1/6. And oops, we got one we don't know. This green box, what the heck?
Would it be 1/18?
That's a good guess. That's a good guess. That's wrong, but you're on the right track. It seems like 1/18 sounds, you're in the ballpark, but think about it, and you're trying to find an antiderivative in a way. Here's the deal. Hey, take a look. If I want to find this guy, okay, this S naught, then I take the derivative of the one above, right? Well, 2 times a half gives me 1. If this 1/2 S naught, let's go above. 3 times 1/6 is 1/2. Just do that again. If I want to end up at 1/6, 4 times what gives me 1/6?
1/24.
There you go. And that's what it is. The mystery solved. That is the new thing for today. That is 1/24. 1/24. Now, so there's something new. I think that if you have a snap, let's say you have a snap of 24, let's keep it simple, and say the snap is 24 meters per second to the fourth, are you going to live? Well, let's say your body undergoes this situation, and let's say the snap knot is 24, the jerk knot is 6, the acceleration is 2. Keep our numbers simple, right? Well, in that case, let's take our time. At 1 second, yeah, you'd be all right. In 1 second, you do move quite a bit. If the snap knot is 24, in the first second, you're going to move 24 times 1, 24 plus, let's say jerk knot is, no. It's 24 times 1/24. So you'd only move 1. This would be 1. This would be 1. 1 plus 1 plus 1 plus 1. So you'd only move 5 meters in the first second. If the snap knot was 24, the jerk knot was 6, the A knot was 2, the V knot was 1, the X knot was 1. You only move 1 meter. But by the time you get to the 10th second, notice this. 10 would be to the 4th power. 10 to the 4th power is 10,000. Here, and also 10 to the 3rd power is 8,000, and it's 100. You would be at 11,111. You would move in your 10th second. You would be at the position 11,111 meters. That would be where you would be. So in 10 seconds, you would go 11. You will have gone 11 kilometers, and not only accelerating the whole way, but your acceleration is accelerating. So you would have certainly a stroke. No human can handle that. So this is sort of an equation for death. And I don't even know if it's possible to make a human go that fast, maybe a particle. Certainly Large Hadron Collider that can do that kind of stuff, but not. So, interesting stuff. Now I want to spend the rest of the time working on the front of 410. Let's finish the front. We'll finish as much of the back as we can. We got 24 minutes. We'll finish as much of the back as we can. The rest will be homework for you to do. You will just make sure you turn it. They're going to get dogs for it. You're going to make sure you turn it in with your packet. I don't want to make you submit anything other than the take-home test. And then take the test next week, turn the packet. All right. And I will get your grades all situated. I'll get the 4A in there, and so you'll still have your cushion. We'll hang on to that till I grade the packet for 4. Here we are on 410. This back in my handwriting days when I handwrote worksheets, but this one I punched into my calculator this equation, and then when I did that, my graphing calculator out pops this graph. Okay. Then I printed it off. I think it was on my old Mac. I printed it off, and here it is. So this is the graph for that equation. It's second order. It's orange, right? Because if it's squared, you're going to get down to 2 derivatives, and then you're going to stop. So this is definitely a trio, but it's not a trio like you're used to. I mean, we're used to these trios right here. We're used to what happened to it? There it is. We're used to these trios like this. We're only seeing, like on the X, we're only seeing part of the parabola, but that's a very simplified view of it. In reality, Trios probably look something like this. So in this case, you start off going backwards, you turn around, it looks like it's 6 seconds, then come back, and you are accelerating. So you start off at the 10-meter mark. Let's say that you're leaving for work, and you get out to your car, you realize you forgot your mask. And so you run back, and as you're running back, you're slowing down, you grab your mask off the front porch or wherever you left it, and then you turn and run back to your car. So that's what's happening here. Okay, with somewhere being the origin, but maybe your car was 10 meters away from something. Anyway, so it's you running back, grabbing something and coming back the other way. What is the initial position of this object? So let's go ahead and answer the questions. So the first one is, what's the initial position of this object? Well, I can look at it and say it's 10, right? It's 10 meters. That's one way of doing it. The other way is look at the equation, right? Isn't that x naught? So it's at 10 meters. What is the direction? What direction is this object going when it starts? Okay, well, I can look at it and say it's coming backwards. So we'll just say it's back to the origin. How about, instead of saying backwards, backwards is a general term, but let's say back to the origin. So it's going back to origin. Doesn't mean you're running backwards. It means you're just moving back to the origin. 3, determine the velocity function. Okay, so now we're going to do the, we're just going to do the derivative. And so we do the x dot here. And I'll just do it down here, x dot. Bring the 2 down, so we have 1/2 t, and then minus 3, right? And that's it, the 10 goes away. And I'll be lazy, I'll put parentheses there and put meters per second. Okay, that's my function, that is velocity, x dot, okay, not average, that's the function. Fine. 4 says, what is the slope of the tangent line at the 10-meter mark? Now you'll need a ruler. Let me find my ruler here. You're gonna need a ruler, not you can't hand do this. You'd really prefer to have a ruler like this, a ruler that's clear. You can see through it. I'm going to now take that and I'm going to try and kiss the curve. I'm going to kiss the curve at the 10-meter mark. Kiss that curve. There's an art to this. Kiss that curve of the. Kiss that curve right there. Oh well. I'll make it green. I like my tangents to be green. That's just my OCD. So, there you go. So that's the kiss. And it says, what is the slope? Now we've got to find the slope of that. Now the slope of the tangent is the velocity, is the instantaneous velocity. So it's supposed to be a straight line. So now I find the slope. Anywhere along here will work. It looks like 2 boxes over is, every 2 boxes is 1. So I'll go over 2. Right there it seems to cross. I'll go over 2. And then I'll go up where it touches. And I get, if I go over 2, that's 1. And then I have a rise of 1 to about 3. Right? It looks like about 3. So it looks like my initial velocity is, it's a negative slope. So my initial velocity is -3. So V naught then is -3 meters per second from doing that tangent stuff. What? Look. I didn't need that. There it is. V naught. The equation told me that. But it was a lot easier doing the equation, right, than doing the daggone tangent lines. Can you imagine how happy that made Newton? No longer did he have to measure tangent lines. He must have gotten so excited that a tiny little smile, little tiny for like 3 seconds, And then he went back to his dour self. 4, what is the slope of the tangent line? Oh, we did that. Okay, so that is the initial velocity. 3, -3, of course. Well, let's go down, because before 6, let's do 5 down here. 5 says to plot the velocity for this x function. Okay. Back to my ruler again. We know it starts at -3. It's got a slope of 1/2. Dun, 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 dun. There. Okay. It goes on and on, or for how long I want it to go. And so that's the velocity versus time. This is very important now. This will help you in the test as well. This is the turnaround. Turns around. And so here it was going, I guess you could say backwards. 4th quadrant. Here it's going forwards. These are all themes we've talked about before. I keep, I'm not repeating myself. I'm just showing it in a different situation. Physics works no matter what. Okay. It says, when does the object turn around? Well, now we see that it turns around at 6. It turns around when it'll turn around when v equals 0, and that's at 6. So that's at 6 seconds. Because if you solve this equation up here, set v equals 0, you'll see that t equals 6.
How did you find the final velocity of the xt function?
You mean how did I know how far to go?
Yeah.
I'll just go out to the end of the graph. Well, the graph looks like the graph goes to 12.5. So I'm just going to go to 12.5 then. I mean, if you want, it's a line, so it just goes on forever until I'm done measuring, basically. So that just keeps going up, and let's make it all the way to the end, 12.5. Good question though. So there is the turn now. No. Okay, hold on a minute. Something fishy here. So we agree that this point is the turnaround point. I mean, it's a child of 5 could see that. That is a turnaround point. Well, let me take the tangent line at that point. Okay, very carefully, I'm going to kiss the curve at that point. Kiss. Tangent line. Now, you would agree with me, you being the jury here, this tangent line, the slope of this tangent, I got to lay out my case here. The slope of this tangent is obviously 0. It's flat. Slope of the tangent equals 0 meters per second, okay, because the tangent in this case is meters per second. Slope of the tangent line is 0. So, stay with me here. Acceleration is v over t. I just proved to you, and you can look at it on this graph too. V is 0 at 6 seconds. So the acceleration, therefore, acceleration at 6 seconds is v over t, which equals 0 over t, which I submit to you, but the acceleration is 0 at 6 seconds. 0 meters per second squared. It's hard to argue with that logic. Therefore, I'm going with something here. Therefore, anytime there is a parabola on the x versus t, and that reaches a maximum or a minimum, the tangent slope is 0, therefore the velocity is 0, therefore the acceleration is 0. So that tells me that if I take this calculator and I throw it in the air, if you can see it, I throw it in the air, and then at the apex, we agree that the velocity is 0. Therefore, I submit to you that the acceleration is 0 at the apex, which means, ladies and gentlemen, we've been lied to since Newton. that gravity, which is the source of acceleration of a object being thrown in the air, we've shown now that acceleration is 0. Therefore, gravity at the apex is 0. So gravity, following my logic, gravity must turn off at the apex of objects. And we've been lied to. I have a buddy named Q. I'm going to email Q tonight and let him know. And we're going to put this on Facebook and all over social media that we've been lied to. And within a couple of weeks, we'll be storming MIT with pitchforks and American flags and QAnon flags. And because we've uncovered a conspiracy of biblical proportions. So somebody talked me off the ledge. Where was my mistake? Oh, whoa. If I'm going to plot acceleration, let's do something else. If I'm going to plot acceleration now, we said that acceleration, and if you do the acceleration, if you do the derivative, back up here. Now, if I take the derivative of this x equation, would it not be 1/2, right? It just ends up, so acceleration, we're saying acceleration is 1/2 meters per second squared. And we're led to believe by this cabal, I'm sure there's some Freemasons involved, we're led to believe that acceleration is constant at 1/2. That's what the powers that be want you to believe, that it's 1/2. But we just proved beyond a shadow of a doubt that it goes to 0. And so in this case, we must redraw all graphs in all textbooks so that they look like this. So that right there, it comes down, boop, boop. And that's how it must be. I can make a lot of money off this idea. All I got to do is get the sheep to follow me. This is why you really don't. You don't want to be ignorant as you go through life, because you'll end up following snake oil salesmen like that. Okay, obviously this is false. What was my mistake? Can you see a flaw in my logic? This is obviously wrong. Gravity does not turn off at the apex of objects. So what's my mistake here? Anybody see it?
The velocity flips from positive to negative.
Yes, it does. But you would have to agree, Miranda, that velocity is 0 as it goes from negative to positive or positive to negative. It's got to be 0 somewhere in there.
Is it because it like constantly is changing, not just during 0, but it's like it turns from negative to positive, so then it goes from negative 0 to positive?
That's it. Velocity, remember velocity, okay, here's the reason why. And you think I'm just messing around here. This was a question on an AP exam about 10 years ago, and it messed up my students because that fooled them on this. But in reality, that is a false, right there, there's a false equation. It's delta V, like you alluded to, like Miranda was alluding to as well. It's going from negative to positive. Yes, it does pass through 0. And so at that instant, you think, well, still, wouldn't it? No, because velocity is a vector. And vectors have two things. Velocity is a vector. Okay, vectors have magnitude, which is the length, and what's the other thing?
Direction.
And so what's happening here to that velocity vector is, it's at that instant it's changing. What's changing about it is the arrow. The direction is changing. You see, when I take something and spin it around at a constant rate, the speed stays the same, but it's still being accelerated towards the center of the circle because we'll get to that. We get circular motion. Actually, you'll get that in AP physics. But as you go around, this is chapter 6. As you go around and around and around, that acceleration vector is constantly changing direction. And that's what makes it, that's that velocity vector, I mean, and that's what gives it acceleration. So in this case, we got to erase that. We don't need to go back and change all the, we can call off Q, and they can all back off MIT now. You don't need to storm it. A congresswoman is not going to get into Congress because of it. Of course, if you're a politician, you would just double down. Double down. And you think this is silly. You know what? This is what happened with the orbit of Mars. Mars, if you watch Mars from the Earth, and they thought they held on to the idea that all planets, let me add this, that all planets orbit, and including the sun, orbit the Earth, right? That was the idea. It just seemed that way, and then that fit the Bible and all. So when you look at Mars, if you assume that Mars goes around the Earth, then you have to put what's called retrograde motion. Mars comes along, and then it appears to turn backwards every once in a while, and then come along, and it turns backwards. So it has this retrograde motion. It's because the Earth overtakes its orbit. And so from our point of view, Mars seems to be going backwards. And so you know what they did? Instead of just going with the logical answer, Occam's razor, going with a logical answer that, oh, maybe the sun's the center. They would not, because of dogma. The dogma ruins things. There's dogma going on in the United States right now. You know, the election was a sham. That's dogma. There's no evidence. It doesn't matter. So because of dogma, they said that Mars had retrograde motion, and they invented out of whole cloth epicycles, that things go around little points. There's absolutely no physics of it. It makes no sense. But it took people like, even Tycho believed this, but finally people like Kepler that said, no, that isn't it. Copernicus, Galileo, that fought it, and Bruno, who died, who's burned to death because he says that's crazy, and they burned him, you know. So this kind of dogma that I was making something up, but it takes hold, and then people can't see the truth. It doesn't matter. The truth is lost. It's always the first thing that's lost in dogma. Okay, so I'll get off I got 4 minutes. Let's take a look at the back now. And the back, we can get this started. The back, we're doing the same thing, only now we have a quartet. So the first thing I want to do before we leave is go ahead and take the derivatives of this x. So take the power rule. Let's do the v, the a, and the j. And we didn't finish this in class either. And so I wanted this to be some homework. But I'll be available on Facebook, of course. But go ahead and now do I apologize for these goofy coefficients, but I had to get the graph to fit into the first quadrant to make it look, you know what I'm saying? So we could talk about it. Anyway, so I apologize. But you can leave them in fractions. Okay, so let's knock these out before we got to go. X dot. I'm buffering. You go ahead and do it. I'm buffering here. Still buffering. You go ahead, I'll catch up. X dot equals V equal. Oh, what a waste of money. It didn't help at all. I still buffer all the time. I'll get my money back. Okay, equals -3/5 t squared plus 12/5 t squared. You can do it as, you can call that 2.4 if you want, minus 1/4, and I'll be lazy, That's meters per second. And then A dot, V dot then is going to be.
Mr. Askew,
Yeah.
on the 12/5, it's just T, not T squared.
2 points for correcting the teacher. Good call. Good call. Good save. That's what happens. I start thinking about something else. Thank you. Plus 12/5. And then A dot is just -6/5. So that's my jerk. Units. Meters per second squared, meters per second cubed. Okay, now we go down here, we got to answer these questions. First off, why the dotted lines? Well, we know that is all imaginary time. And I've got 2 minutes still. It's imaginary time. Talk to Paul Dirac about that one. And then over here, this is when is the velocity maximum? This is the last thing I'll do. When is the velocity maximum between V0 and V5? So V0 is right. V0 is right here. V0 is right here. V5 is about right there. And when do you, what time? Give me a time. When do you think the slope is the velocity of this? When is the slope the greatest?
At 4 seconds.
4 seconds. 4 seconds, I say the position is the furthest away, but that's not the slope.
I was gonna say at the mid time.
At the mid time. Okay.
Or like mid, like 2.5.
Yeah, it's the mid. Yeah, it's the mid time between the maximum and the minimum, right? And those of you that are in pre-calc, maybe calculus would know this. That's about right there. What do we call that point? What's the name we give that very special point? It's called the
point of inflection.
There it is. Give yourself the point. Point of inflection, POI. And this is on question 9 on the take-home test. That's called the POI, and that is the steepest slope. That's where the most change is happening. Last thing. So Dr. Fauci was talking a couple nights ago, and he said, I think we're at the point of inflection. Actually, this is a while back. This is a few weeks ago. He said, I think we're at the point of inflection for deaths. It'll start to come down again. He was right. It is. Now he's worried it's going to come back again with all the strains. So, but he said that's when, he said the point of inflection where we're getting the most deaths per day. And then sure enough, he was correct. It started trailing off after that because they follow this stuff. They're listen to these people. They know what they're doing. So anyway, that's called point of inflection. I guess the rest leaves the rest to you. I am not leaving you. I'm available on Facebook. Sometimes it takes me an hour or two to finally see your question, but be patient. If you really are in a hurry, you can text me and say, could you please answer this? You know my number. I can't give it to you because this is public, but you can message me for my number if you want and text me if you need to. Okay. Good class. Good class. See, that's as far as we got in any class. We're all about the same place. That's good. So this weekend, do that. Work on your take-home test. I've got the key. Ready to answer your questions on Facebook. Be safe this weekend. The strains are here in Oklahoma, I'm convinced. And I think you need to be extra careful for your parents' sake and your grandparents' sake, if not your own. All right. So, love you guys and all. And I'll see you guys Monday.